did you kill me? No, I am your father. No, it's not true. That's impossible. Such your feelings. No, it can be true. No! And if you close your boots and your motorcycle, you forgot to say please. A census taker once tried to test me. I ate his liver with some fava beans, and a nice Chianti.
Heute Abend ganz herzlich zur Eröffnung der neuen Sonderausstellung Genial und Geheim, Alan Turing in 10 Etappen im HNF begrüßen. Dear Dr. Hodges, we are very proud to have you here tonight in Paderborn on the opening of our special exhibition on this legendary computer scientist and codebreaker Alan Turing. Ziel dieses Ausstellungskonzeptes ist es, durch hochwertige, selten verliehene Exponate und interaktive Installationen, verknüpft mit historischen Multimedia-Collagen, die Besucher zu einer Auseinandersetzung mit Alan Turing und seinen vielfältigen Forschungsfeldern zu motivieren.
Außergewöhnliche und einmalige britische Forscher Alan Turing hat in vielen, vielen Gebieten gearbeitet und hat in vielen Gebieten die Grundsteine gelegt. Zum Beispiel im Bereich der Berechenbarkeitstheorie, hauptsächlich die grundlegenden Definitionen der Berechenbarkeitstheorie gehen alle auf Alan Turing zurück. Im Bereich des Zusammenhangs zwischen Logik und Berechnung, in der künstlichen Intelligenz und auch in der Morphogenese.
Also das Alan-Turing-Jahr, dieser Zeitraum von einem Jahr, das muss ich direkt mal vorweg schicken, haben wir uns nicht ausgedacht. Also da gab es eine Vorgabe, dass man eben ein ganzes Jahr dem Mathematiker und Computerpionier Alan Turing widmen möchte. Und der eigentliche Grund ist, dass Alan Turing wirklich ein Kopfmensch war. Das ist hier illustriert von einer sehr schönen Zeichnung von Jim Wickett aus dem Jahre 2002. Er hat sehr viel, oder er hat eigentlich in erster Linie theoretisch gearbeitet. Er hat wichtige Veröffentlichungen gemacht, er hat bahnbrechende Entdeckungen im Bereich der mathematischen Logik, in der Computerwelt und natürlich seine Arbeit als Codebrecher in Bletchley Park. Und in diesen ganzen ersten beiden Etappen geht es im Wesentlichen natürlich um die Geschichte der Enigma, die Verschlüsselungsmaschine, die die Deutschen im Zweiten Weltkrieg insbesondere auf der operationalen Ebene eingesetzt haben, die auch in den U-Booten eingesetzt wurde. Und dieser Kriegsschauplatz, da möchten wir eben einen Fokus drauf legen.
Is Alan Turing in 1936 his great moment when he defined Turing machines, computability, and the universal machine. He was young, he was full of energy, he was rowing, running, playing games, and full of fun, full of jokes. And these are things that he learnt about, the nature of the physical world, directly from Einstein and from Eddington, the foundations of quantum mechanics from John von Neumann, the mathematical philosophy and logic from Bertrand Russell, and most excitingly for him, Gödel's 1931 proof of the incompleteness of logical systems. In 1937, Alan Turing worked at Princeton on an electrical machine to implement a cipher system, but we don't know what it was. He left no notes. It's disappeared. But we do know he was very aware of the world political situation. He was very aware of refugee German scientists in Cambridge and at Princeton.
we are very glad to present you the HNF Turing machine, which is a real machine demonstrating the basic concepts of computation, designed by Alan Turing in 1936 when he published his very famous paper on computable number with an application to the Entscheidungsproblem. And we used these ideas to build a real machine that is on display here in the Heinz Nixdorf MuseumsForum, and this machine, as well as some other machines, will be part of the exhibition on Turing machines in September. Okay, what we see here is our model of a Turing machine, and this is a very interesting concept introduced by Alan Turing in 1936 in his groundbreaking papers on computable numbers. And in this paper he proposed a special machine as a mind experiment, an automata, which was able to calculate all things that can be calculated in general. So I would like to give you a short example for this. Think of simple addition, for instance. If you would like to add two numbers, you have a clear understanding of how many steps you would need to fulfill the addition. Well, this is a very simple example that can be performed on our Turing machine here as well. A more difficult or sophisticated task is to calculate the number p, for instance. We all know that we have infinitely many digits for the number p, and in this case such a computing machine won't stop with the calculation because there is no end. Whereas for addition there is an end that can be calculated. And our Turing machine indeed has all important features of the original Turing machine, although it has not an indefinite tape here. So we see the most important components of the Turing machine. We have a tape which is able to store data. In our particular case, we have a very simple tape that can show two different states. We see the metal things here, and we can put two different states on each tape element. The second important component of the Turing machine is the read and write head. We see the read and write head here, and this machine is able to operate the tape. So the tape can be moved forward and backward, and the head, the read-write head, is able to detect which state is on the tape, and eventually it can switch or change the state of the machine. And I would like to show you a very short example of a very short addition that can be performed by our HNF Turing machine. I can start the addition here with a touch screen, and I would like to show you a very simple addition. For instance, we are going to try to add the number 2 and the number 2. And I start the machine right now. So we see the Turing machine, our Turing machine starts working. And in the first step, we have put the number 2 on the tape. We see it right here. And here is the second number on the tape. And now we bring both entries together. We delete 1, 0 and switch them together. So the machine is able to read the state, to readjust the state, and to move the tape forward and backward as intended by Alan Turing. And in the end of the task, we see that the machine wrote the result of this addition on the tape. We see the 4 digits here in the beginning of the tape, and in this case the machine fulfilled the task after a limited number of steps. And it was a very interesting question Turing and other people in this era addressed, if all calculation will stop when using this Turing machine. And now we know that indeed there are calculations or computations that won't stop. A very prominent example is the calculation of the number p, for instance. Other tasks are more easier to understand and to perform. And amazingly, all of our computers we are using today are in the heart of the machine such Turing automata, such Turing machines. This is the basic principle that drives all computation we are using every day when we using our smartphone or when we are gaming on the PC. So we have, of course, more tasks for the machine. We can do subtraction, multiplications and divisions as well. And again, for this special calculations, we know that we find the result within the finite number of steps. And so more sophisticated tasks can be done by this Turing machine. We are very glad that we can present this machine in the Alan Turing year 2012.
Yeah, my name is Horst Zuse. I'm coming from Berlin, and I'm the oldest son of Konrad Zuse, my father. And I will talk a little bit about his developments of his computers or calculating machines at this time. And I will start with Z1, which development started in 1936. And this is a very interesting machine from a technical viewpoint. Why? It is a floating point machine, a binary floating point machine with 22 bits of the mantissa and 7 bits of the exponent and 1 sign for the mantissa. The sign of the exponent was integrated in the exponent. It is a machine programmable, freely programmable, and it has a memory of 64 numbers. And the arithmetic unit was realized with addition, subtraction, multiplication, and division. The very interesting thing of this machine, the Z1, finished in 1938, it was realized with metal sheets. There was only an engine to make the movement of the metal sheets, but there were no electrical switches in this machine. Another very interesting point of this machine is the realization of the addition. That means we have there a kind of carry ahead. That means the transportation of the carry from the right side to the left side, and it was done mechanical. The input and output devices of this machine were realized in a decimal form. That means decimal floating point numbers. And the translation, for example, of the input device was done by the arithmetic unit from decimal floating point numbers. The machine, the calculations which the machine did were done binary, and then there was a translation back from the binary floating point system to the decimal floating point system. The problem with the Z1 was the functionality of the metal sheets, and this was a problem. It doesn't work very well. Another very important point is here to say that the Z1 was financed privately. The interesting thing of the Z1 is a high similarity to the proposals of John von Neumann in 1945. There was a separation of the unit, the arithmetic unit, the memory. It was a binary memory. That means you could store numbers and theoretically you could store digits and alphanumeric digits. And there was a memory, there was a arithmetic unit, there was what programmable, it was a binary floating point machine, and it had input and output devices. That is very interesting. The only difference to the proposal of John von Neumann in 1945 is that the program was not in the memory. It was on a punch tape. However, at this time it was really not possible to put the program in the memory of the machine because the capacity was not enough. In 1939, he began with the development of the Z3 with telephone relays, and the architecture was almost similar to the first one, the Z1. There was only one difference. This was the technical realization of this machine, and the arithmetic unit had additional the square root. That was the only one difference. And this machine he could present in 1941 in Berlin at May 12. And all the other things are identically from an architectural viewpoint to the Z1. Z1 and the Z2 was a testing machine for telephone relays. And in the Z3, everything was realized with telephone relays. And in the Z1, this is a difference, everything was realized with metal sheets. However, both machines, the Z1 and the Z3, were prototype machines. And they were not used for calculations during this time, or practical calculations. Then the Z4 did follow. On the architecture, technical realization of the Z4, it started in 1941. It was a task by the Henschel Aircraft Company in Berlin. It was very similar to the Z3. Telephone relays, but there was one difference. And the difference was he did use again metal sheets for the memory of this machine because he wanted to have a very small memory. It was 1 meter in the square. And the Z4 consisted of around 2,500 relays. However, the memory was again realized with metal sheets. That was not the case in the Z3, where the memory was realized with about 2,000 telephone relays. So, what was the reason for that from a technical viewpoint? The Z4 had a word length of 32 bits. That means a very high accuracy of the number system. Again, the Z3 had a word length of 22 bits, and so the Z4 was for a scientific calculation very appropriate. So this machine, what was another difference? There was no other difference to the other ones. It was bigger. There were a lot of other numerical calculations realized in these machines. For example, the division by 5, the division by 7, and the multiplication, so that this machine could work very fast. And this machine was realized was finished in 1945, but did not work till 1945 in any way in Berlin. It was a very long development of this machine. And this machine C4 in 1950 was delivered to the university in Zurich. So we had, I did talk about the machines C1, C2, that was not very important because this was testing the telephone relays, but the Z3 was very important because it is accepted as a very important machine today. And then I did talk about the C4. And the interesting thing is that he did not change the architecture of his machines from the 3.1 to the C4 in a major way. It was always almost the same. And with the exception of the C2, that was a fixed point machine. It was for testing. But as I said, the Z1, the Z3, and the Z4 were floating point number machines. That was his principle from the beginning. All these machines had two registers for the arithmetic unit, and there he could make his calculations. Later, beginning with the 50s, he did take the same architecture because it was a good idea. And this machine here, the Z11 from 1955, was the first computer in Germany, and it was produced in 46 pieces. The price was 100,000 D-Mark. And the interesting thing is it was again a floating point computer realized with telephone relays and stepwise relays. And the stepwise relays you can find in the Z3 to make the, for example, the multiplication and division and the square root by additional additions or subtractions. And the Z11, it was the same principle. Floating point machine, a word length of 38 bits. That means a high accuracy of the numbers. So let's make a final statement to his computers or machines from the Z1 to the Z11, which was the last one from 1955. The principle was the separation of the units, control unit, arithmetic unit, freely programmable, a memory, and the important thing, floating point numbers in the binary system. And he is not the inventor of the floating point numbers, that means Konrad Zuse. However, he implemented it consequently in his computers from the beginning in 1936. And I think, from my viewpoint as the son of Konrad Zuse, that is really amazing that he did it. Thank you.
It's a pleasure for me to stand here at the Heinz Nixdorf MuseumsForum to talk today about Alan Turing and Konrad Zuse. Alan Turing was born in 1912, Konrad Zuse was born in 1910. So they were contemporaries, and they were working on two different countries. They were working on two different fields. Alan Turing on mathematics, Konrad Zuse was getting a degree in civil engineering. But at the end, they were both working on the same topic. That's the computer, the invention of the computer. Alan Turing was a pioneer regarding the concept of computability, because at the time, nobody was certain what computability was. So there were different approaches. For example, the approach followed in Princeton with the lambda calculus by Church. He developed a calculus for transforming expressions, written expressions, in other expressions, and it was possible to express numbers and functions using this calculus. Alan Turing was a more practical person. He started thinking about the way mathematicians develop their theorems, and he said, if we are going to work with mathematics, we need a paper, we need somewhere where we can write the numbers down, we need a pencil to modify these numbers, and we also need a processor. That's our brain, which is just changing the symbols on paper. That was the prelude to the conception of the Turing machine. The Turing machine consists of a long memory, which is only capable of containing 1 bit at every position, that's zeros or ones, and a small processor which is transforming those bits according to different states. So the processor can change state according to the bit that has been read, and during the change of state can write down another number, another bit, and continue moving to the right or to the left. That's the essence of the Turing machine. So what is surprising about this very simple machine is that Turing could prove in 1936 that you could write programs, you could write state transitions and put them all together, so that the complexity of the machine is moved down to the software. So the machine is very simple in the hardware. The electronics for building such a Turing machine would be very simple. But the programs are long, the programs take care of the complexity, the programs allow you to write down actually any computable function you would like to compute. And that's why today when we talk about computable functions, we say a function is computable if it can be computed by a Turing machine. Now, Konrad Zuse, when Alan Turing was doing all of this in Cambridge and Princeton, Konrad Zuse was working in Berlin. He was interested in developing a computing machine or a desktop calculator for the engineer. And he was not really an expert in all the logical details of this endeavor, but he was a mechanical genius. So his first approach trying to develop a computing machine was not to take electronics, was not to take telephone relays. His first approach was to develop a mechanical computer. Some pieces of these mechanical computers can be seen in this exhibition, where the movement of the mechanical pieces is such that a 1 is expressed by a movement to the right, for example, of a bar or just a piece of metal, and a 0 is expressed by a movement to the left. So 0 or 1, just two movements. And the complexity of the machine, or the main problem here, is to connect all these mechanical components in several levels, because there are several levels of action with many different components, thousands of components, so that he could have a memory for 64 numbers, read those numbers to a processor, put those numbers into registers, and then compute the addition or subtraction of the two numbers. So that's the main operation, that's the basic operation in Konrad Zuse's computers, addition and subtraction. Multiplication and division are built of repeated additions and subtractions, and even square root. The square root of a number can be computed in this way. The first machine developed by Konrad Zuse was the mechanical C1. The second machine was the C2. It was a prototype, and the real interesting machine for showing, for asking for funding was the C3, which was a machine built with relays. Here I have a copy of a portion of the C3, where you can see that we have two numbers, two registers, and then in 3 stages of logic, the addition of these two numbers can be computed in just one pass. So it's a very elegant design, it's a very elegant machine, and this was the machine which was shown in 1941 and which allowed Konrad Zuse to ask for funding for a bigger machine, for the C4, which was finished in 1945. Now there is something that is not obvious from this history of the machines, and that's the fact that Konrad Zuse was not just thinking of building big machines for handling many numbers and doing the arithmetical operations, but he had a very clear understanding of the levels of complexity in computing machines. So his idea was that you could write a program in for example, in a complex programming language, and in fact he developed the first programming language of the world called Plan Calcul. So you could write a program using the expressions of a high-level programming language. Then you could transform this in smaller instructions or simpler instructions, like the assembler we have now for microprocessors. And then you could transform each of these instructions into even smaller instructions, micro instructions, as we say today. and use these micro instructions to tell the hardware how to break down complex operations into simpler operations, simpler movements of all the components of the machine. At the end, if you continue decomposing the high-level program into even ever simpler instructions, you come down to a very simple machine, a machine which is only capable of doing 3 logical operations: the conjunction, the disjunction, and the negation of 2 bits. The 2 bits are put in registers, and the 2 bits are loaded with bits coming from a 1-bit memory. So you can think of this very simple machine as a very long memory where you can only put 1 bit. Then anytime you want to compute using these bits, you load 1 bit to one of the registers, just 1 bit. Then you load another bit to the second register coming from any one of the addresses, memory addresses in this memory. And then you can combine them using a conjunction, a disjunction, or a negation. And then you put back the result in the memory. So that's the way the simple machine conceived by Konrad Zuse should work. It was called the logic machine or logistical machine, and it consisted of just this memory and this very simple processor. And there was a back and forth movement between bits going from memory to the processor, being transformed and back. The whole complexity of the machine was in the program, in the software. So the program was to be contained in a punch tape. So you would have a punch tape reader. The punch tape reader would read if you wanted to do a conjunction, a disjunction, or a negation, and would act accordingly. The machine would be very simple. The program would be very large. Exactly in the same way as was done by Turing in the Turing machine. So there you also have a very long memory, an infinite memory in the case of Turing, and a very simple processor. It's astonishing for me that from the beginning, that means from 1936, 1938, Konrad Zuse had already thought of the logistical machine. Even before finishing the C1, even before building the C3 and the C4, he had a clear conception of what he wanted to achieve. And then at the end of all, this main period of creative work of Konrad Zuse from 1936 to 1945, he came back to the beginning. He wrote a patent application for the logistical machine, and he wrote down the instruction set of the Planck calcul. He closed this period of creativity by going back to the simple machine, or a very simple machine of the same kind that Alan Turing had dreamed of in 1936. That's the connection that we can find between the work of Turing and the work of Konrad Zuse. It's a surprising connection, it's a very interesting connection, and it's something the computer scientists should be aware of. Thank you.
During World War II, Alan Turing played a crucial role in deciphering German military intelligence, encrypting using the Enigma machine. Many people are, however, unaware that he visited Germany on several occasions and entered into scientific correspondence with Germans. Andrew Hodges writes in his biography that Alan Turing was able to read German texts. He requested a copy of the Mathematical Foundations of Quantum Mechanics by John von Neumann as a school prize before embarking on his studies. Presumably, he subsequently also read The Principle of Logic by Hilbert and Ackermann in the original. This is the work in which the Entscheidungsproblem, decision problem, immortalized in the title of his epochal article on computable numbers with an application to the Entscheidungsproblem, is defined. Alan Turing first visited Germany in the summer of 1932, a year after embarking on his studies. He and his father spent 2 weeks hiking in the Black Forest. 2 years later, in June 1934, he and his friend Dennis Williams went on a cycling tour starting in Cologne. In Göttingen, Turing consulted an authority, presumably on the subject of the central limit theorem, that was also the topic of his ongoing dissertation. A first scientific contact to Germany was established in 1937 after Turing had published his article on the solving of the Entscheidungsproblem using the idealized machine that subsequently bore his name. At the time, Heinrich Scholz occupied the first German chair in this field at the Institute of Mathematical Logic and Basic Research at the University of Münster. In February 1937, when Turing was already working with Alonzo Church in Princeton, he was sent a postcard by Heinrich Scholz asking for a copy of his work. On receipt of the work, Scholz wrote to Turing in March 1937, "The method you have used to demonstrate the insolubility of the Entscheidungsproblem, even for Hilbert's first-order predicate calculus, is so fine and original that I have resolved to have presentations submitted on your work in our logistical study group." The institute in Münster led to an indirect contact between Turing and Germany during World War II, thanks to Gisbert Hasenjäger, who later achieved doctoral and postdoctoral qualifications at Scholz Institute before transferring to Bonn in 1962 to establish the Seminar for Logic and Basic Research. As a young soldier, before he studied mathematics, Hasenjäger joined the encryption department of the OKW as its youngest member on the recommendation of Heinrich Scholz. During the war, Hasenjäger was the only German expert to be entrusted with reviewing the security of the Enigma used to encrypt tactical military and navy intelligence at the OKW in Berlin. He claimed to have managed to crack several codes. Long after the war ended, when the events at Bletchley Park became known in the 1970s, he was astonished to discover that his most prominent counterpart was Alan Turing, and he regarded this in a positive light. Had this not been the case, the war would presumably have dragged on for longer, and the first atomic bomb would have fallen on Germany instead of on Japan. Tommy Flowers was the builder of the Colossus decryption machine used to decipher strategic OKW intelligent encrypted using the Lorenz SZ42 or Siemens Geheimschreiber secret writer. He and Alan Turing visited a laboratory in Franconian Switzerland 4 weeks before the end of World War II. They were traveling as part of a TICOM mission, one of the aims of which was to examine the cryptographic and cryptoanalytical methods used in German intelligence communications. Their destination was Burg Feuerstein, where Professor Oskar Vierling headed a previously secret research laboratory whose employees were working on various projects involving wonder weapons. Turing and Flowers, who did not reveal their identities to Professor Vierling and his staff, were most probably interested in projects involving voice encryption. These included the development of secure voice encryption devices and enhancement of the SZ42 encryption machine, whose codes had been broken by the Bletchley Park cryptologists at the start of 1942 with the help of Colossus. Turing himself had developed a portable voice encryption device known as Delilah between May 1943 and July 1944. In the late summer of 1947, Alan Turing traveled to the British occupation zone in Germany with a group of English computer specialists, including John R. Womersley and Arthur Porter, on a mission to acquire the computer know-how of the German experts in the field. The group was from the National Physics Laboratory in Teddington, where work had just begun on development of the ACE vacuum tube computer. The British contingent put their questions at a colloquium at Göttingen. The German participants they had invited included Konrad Zuse, Alwin Walter and Helmut Schreier. Heinrich Scholz clearly got in touch with Turing again in the 1950s. Evidence of this is provided in the form of a dedication by Turing in a special copy of his work Computing Machinery in Intelligence, which still is kept in Münster.
Attempts by Scholz to invite Turing to a conference in Münster in 1952 were initially rejected by the Foreign Office in London, which subsequently authorized a visit from February 22nd to 25th, 1953. Turing himself proposed 3 lecture topics. First, unsolvable problems. Second, electronic computers in England. Third, the chemical basis of morphogenesis. However, Turing fell ill and was thus unable to travel. All subsequent attempts to invite him failed. Another mark of the huge significance of Alan Turing and the esteem in which he was held at the Institute in Münster can be seen in the fact that there was a Turing room devoted to him from 1960 to 1985. Gisbert Hasenjäger and Dieter Rödding were the people who brought it to life. This room featured publications, presumably including the special copy of computable numbers, as well as models of Turing machines. Happily, a large number of the artifacts from the Turing room were kept privately by Hasenjäger's and Rödding's wives and recently handed to the Heinz Nixdorf MuseumsForum in Paderborn for reconditioning. The Heinz Nixdorf MuseumsForum in particular possesses 2 Turing machines from the estates of Professors Hasenjäger and Rödding. One universal Turing machine with fixed connections and 4 states and 3 tapes, and one modifiable Turing machine with 28 relays and 6 tapes. The universal Turing machine has recently been analyzed by German computer scientist Rainer Glaschik and currently is on exhibition at the Isaac Newton Institute in Cambridge before going on show at the Heinz Nixdorf MuseumsForum in Paderborn as of the end of July 2012.